So first and foremost, all of your exams are finally graded. I sincerely apologize for the delay. Please do take a look at your exams and the feedback I gave you, even if you got full points. So the most common thing that I commented on was this appearance of numbers being divided without any introduction as to what's being done. So it's really important when you're doing your work is that your work stands alone, that I'm not left to guess at anything, particularly when it comes to defining your axes. So I let it go this time, but for forces, it's critical that you define for me what is positive and what is negative. One of the things that concerns me when I see people randomly writing in negative 9.8 for gravity is that what tends to happen if you're not making a conscious decision with that is that you double enter in that sign, specifically when we're dealing with forces. So in other words, if I've already defined down as negative and my force due to gravity is pointing down, when I set up that equation, I've already accounted for the fact that the acceleration due to gravity is negative or going in what I've defined as a negative direction. If I then put in that negative sign again, now I have the force of gravity doing something totally opposite of what I intend. So be very conscious of when you put in your signs. For your work, I'm not looking for numbers to show up. I want to see that you understand what you're doing. And so do take a look and let that feedback kind of guide you for the exam we have coming up this Friday. And this Friday's exam will be on forces, including center seeking forces. And that also will include then motion, right? So if I have a net force causing some acceleration, I should be able to then apply that to equations of motion dealing with that acceleration, so long as it's constant. That was probably one of the more common errors, is that if I gave you an equation describing acceleration, then that means that it's not constant. So you can't just determine what acceleration is at some given time and then extrapolate that out to everything else. But I will tell you, for this particular exam, there won't be a changing acceleration because I'm focused specifically on forces and how that changes things. So what we're doing this week then is energy and work, and that will not be on this exam, that will be on the final. Hopefully some of you got to watch at least most of the videos dealing with work and energy. So I am working on the handout that I wrote on the module, that these are the examples that we will be working on. So if you're wondering where we are, just go ahead and go to the module and open the link for the examples today. And what I'm going to start with to get us thinking about this is this example 5. It's one of the more common problems that you see because it incorporates so much. So the important thing to remember here is that even though we're switching to work and energy, well, work is nothing but a force applied over a distance. So all of the work that we've done up till now, pun intended, is all wrapped into this. We're not abandoning anything we've done and doing something completely different. This is just extrapolating out more of how we can capitalize on solving different physics issues. So for this particular one, I have this little mass is going to go, you can think of it as a marble. It's going to slide down this ramp and go on a loop-de-loop. And what we want to figure out is how high up on the ramp does it need to be to just make it around the loop-de-loop itself. So what I want you to do, I'm going to send you into breakout rooms. We're going to take just 5 minutes. And I want you to first to think about this in terms of what forces there are at different points on this track. Specifically, what forces do I have at the top of the loop-de-loop here? And what forces do I have when it's kind of on that curved incline right there? So first do that. And then the second thing is define for me what kind of energy I have. So this point here, we'll call this point A. It's going to be me holding the ball in place. So I'm getting ready to release it. It's not in motion yet, but up here, we'll call this B. It is in motion. So I want you to label what kinds of energy I'm going to have at both points A and B. And then we're going to come back in and work on this specifically. Does everybody understand what I want? Cool. Pause recording. Okay, let me share my screen. So let's see, we called this point A and this point B. So let's start with our forces. What forces do we have going on at point A?
Force of gravity and normal force.
Good. So I'm going to have, like, in this particular case, it's probably easier just to draw it on there. I'm going to have my force of gravity going down. Now my normal force, again, is always perpendicular to the surface. So no matter how odd shaped that surface is, just do your best to do a perpendicular line there. And there's my force normal. Now what about B? A.
That's just all force of gravity, right? Just not a normal force?
Correct. So what I have going on there, if I'm just going to make it, when you see words like that, that means that I'm losing contact with the track. Now, let me ask you this. This is probably one of the trickier parts. If I say I'm just going to make it, do I have any kinetic energy? In fact, let's start with B. So at point B, then I have just the force of gravity down. Now, energy. Actually, let's start with A. Let's be consistent. So for A, what kind of energy do I have there?
That'd be gravitational potential, right?
Good, good. So gravitational potential means that I am some distance higher from the force of gravity. I'm sorry, higher up from, okay, wait, let me start over. I think of a good way to word this. Here's the Earth. There's the force due to gravity points down straight towards the center of the Earth. So when I look at, let me do a better circle.
I have a quick question about the forces at point B. Since the ball never leaves contact, wouldn't there also be a normal force perpendicular from its point of contact on the track?
So if I kind of led you astray there, this question is to maintain contact. So if it is going to just maintain contact, we look at the point just after it loses contact. So in that case, we would say that the force normal is 0. Anything faster, and it will maintain contact. So we're kind of just looking at that threshold between 0 and touching. Does that make sense?
Okay, yeah.
It's some of the wording with energy can get tricky. Okay, so for potential energy, my horrible circle here, the distances that we're doing relative to is we're saying, okay, so the force due to gravity is the center of mass to center of mass attraction for something small to something relatively large. It can be you, it can be a box, it's all relative to the center of the Earth. So if I move from on the surface of the Earth, I have this force of gravity. What I'm looking for in terms of potential energy is any height change. So if I go from being right on the surface to say just this point above it, my difference in potential goes from how much potential energy I have being on the surface compared to however high up I've moved. And the reason why I'm emphasizing this is the one thing that I notice when I work with students is that getting kind of this relative comparison can be really tricky. So I can look at the difference in potential energy from holding a ball above a table and dropping it onto the table. So that height difference is the potential energy I have. Or I can hold the ball at the same height, but move it away from the table and then drop it. So now the height difference that I'm looking at is how much potential energy difference is there from the height of my hand to the floor. So I can make these things really relative to what I'm comparing it to. So in this case, I have potential energy from height, from gravity. And that potential energy difference is comparing this height here to, if I can draw that line, kind of extrapolate out to the track on the ground. Does that make sense to everybody? And for potential energy related to gravity, well, that then becomes, let's see, mass times gravity. And when we deal with work, it's always a force over a distance that gives us an energy. So this is my force due to gravity, and then my distance is just going to be that height change. So you can consider that like a delta y or an h, but I can make my zero wherever I want when I'm comparing it from one point to the other. Is that clear to everybody? Okay. So then now let's look at point B. Let's see, I have, somebody said I have potential energy due to height. Is that what I heard? Do I have anything else energy wise?
You'd have kinetic energy, right? Because it's
Yep.
moving.
Yep. And that's the tricky part that I started to kind of get ahead of myself on, is that when we hear that it's going to just lose contact, one of the more common errors is for people to then say, oh, so this velocity is zero. If its velocity is zero, is this, and we're talking tangential, is the ball going to continue going in a circle? No, it's going to drop straight down. So when we're looking for a minimum, we're not saying when the tangential velocity is zero, we're looking at what that tangential velocity is, essentially just kind of enough to continue carrying it in the circle on the ramp. So it's going to temporarily lose contact and then continue back on the ramp itself. So we've identified the forces. Let me do a sum of forces here for B and the Y. And we'll just do, no, I'm going to not do up. It's reminding myself that my acceleration for center seeking force points towards the center of the circle. Therefore, I'm going to go down is positive because my acceleration is going to be coming down towards the center of the circle. So I'll go down and to the right is positive. So we only have one force there. That's the force due to gravity. What is that going to equal? Does it equal MA, zero? What do we got going on there? And can it equal zero? Let's start there. I have one force. Can my sum of forces equal zero?
No, unless that force was zero.
Yeah. So unless the force like a massless particle, so that gets us nowhere. If I have one force that I can identify, then I do not equal zero because I have a net force. So in this case, do I equal MA? Do I equal what? It's not zero.
This mv squared over r.
Perfect. So remember, mass times acceleration for net force. If I'm going in a circle, which in this case I am, then my acceleration is defined as v squared, the tangential velocity over the radius of that circle. Cool. So let's see. we want to define the height this thing has to be. So what can we do? I can look at my forces, I'm sorry, my energy before and after. And so I think I'm just going to start there. Page up, give myself some room here. Let's start there. I'm going to say, okay, what I'm doing is I'm comparing the energy I have before to the energy I have after. So I can turn this now into an equation and be like, okay, so I have potential energy initial plus, well, let's see, we're talking at point A. Well, all I have is potential. I don't have kinetic. So actually not plus anything. What's this going to equal to the energy in the end? So if I don't have anything zapping energy out of the system, then what I have in the beginning is going to go completely into what I have in the end. So what do I have in the end? I have this potential energy, we said, because it is at some different height. So I have final, and then plus this kinetic energy. So let's go ahead and turn these things. Now, kinetic energy, just in case you haven't had a chance to watch the videos, is defined in terms of 1/2 mv squared. And we kind of derive where that comes from in the earlier videos. So take a look at that if you're curious. All right. So what do I have? I have mg and then h1 for h initial, however I want to define that, is going to go to mgh2 plus 1/2 mv squared. And then I get excited. Things cancel. Let's go ahead and cancel out our masses. So I get gh1 equals gh2 plus 1/2 v squared. And then I look at this and I'm like, I don't know what velocity is. I want to know what height I need to launch the ball from. This is where I can reach in back into my forces that we did. And this is why I asked you to do both, because oftentimes we're going to need both. And I look up here and I'm like, okay, so I've defined the force due to gravity in terms of v squared. So let's see if I solve that, and let me write it out. So I'm going to have mass times gravity equals mass times v squared over r. Well, r is just h2. So I can rewrite this as h2. And my masses cancel. So I can see then that v squared equals h2 times g. Does that make sense to everybody? Any questions there? Okay, so I'm going to make that substitution. Then I get gh1 equals gh2 plus 1/2 times h2 times g. And then I get all excited because something else cancels out. Gravity. What? So this whole thing simplifies down to h1 equals, let's see, I have 1 plus 1/2, so 3/2 h2. And that's it. So this is very idealized. This is saying that h1 needs to be 1.5 times higher than h2 in order for me to just make it around. And we took something that looks like we have like absolutely not enough information to solve for, and we're able to pull it down and simplify it to this really pretty equation. So everybody seeing kind of the logic there?
I have a question about the equation that you have written. It's for the whatever it's called, the velocity that points towards the middle of the circle.
This one?
Yeah.
Okay.
So I thought the equation was mass times velocity squared over the radius, and isn't the height of the ball, isn't that actually the diameter? So when you have to divide it by 2.
Oh, thank you. Yes. Woo, good catch. Yeah, I made a mistake there. All right, so let's go back. So here is the radius and the height is, so H2 equals 2R. Or what we want is R equals H2 divided by 2. So let's go ahead and fix this starting here. That I get G equals MV squared over R. So, oops, no M, we cancel that out. Equals V squared, let's see, divided by H2 divided by 2. So equals 2V squared over H2. So let's see where we made that substitution. So what do we get over here? Cross this piece out. So I go, it was H2 plus 1/2 times H2, or I'm sorry, times our V squared. That's what I didn't do. I'm sorry. Let me back up. I want to define this in terms of the H2. So H2 equals 2. Why did I do this to myself?
Should equal 2V
Yeah.
squared over G, yeah?
Yeah, I very much. Yeah, that's H is. I'm sorry, go ahead and say it again. My brain just totally vapor locked on me.
H2 should equal 2V squared over G.
There we go. 2V squared over G. And we want V squared. So G H2, there we go. Now I'm happy. Divided by 2 equals V squared. Any questions? Because I just made my brain go short circuit. So if I've left you lost, speak up now. So let's address that.
This is just kind of about the force of the, I've always forget what to call it. But can you always apply it when there's an object moving along the path of a circle and
Yes, the center seeking forces.
center seeking force?
Yep.
And so it's always applicable as long as
As
for
I'm
some
turn-
reason it's turning around a circle.
Yes, yes, absolutely. So I'm going to start here, clean. I get G H1 equals G H2 plus 1/2 times my V squared. My V squared is G H2 divided by 2. And then once again, my G's cancel. I get H1 was H2 plus H2 over 4. Let's see, so 4 over 4, 5/4. H2 is our H1. There we go. Thank you for catching that. So going back to it, the one thing that was just asked is, yes, if I'm going in a circle, I want to do something that does my sum of forces in that circle. Because the beauty of that is I get that V squared term. And when I'm dealing with energy, if I have something in motion, I'm going to have that 1/2 MV squared. So that means I can relate those two things and simplify things down in order to eliminate some variables. So I can tie things into each other. Does that make sense to everyone? We do have time. So the next one I'm going to do is this example number 6. For this one, I'm going to give you 6 minutes in the breakout room. Again, what I want you to do in the breakout room is define what I have energy-wise at point A. And then let's see, we want to know what the energy is after I've crossed here. So point B. And there's something specific that it gives us. This one we have this force of friction patch, or I'm sorry, a friction patch, a rough patch, if you will, that the block is going to slide over. And this one wants to know how high I need to be in order to get that velocity at the end. So start by defining what energy I have at point A and point B. And now let's think about how you can relate that friction piece. And so what I want you to do after you've defined that is to set up something like this for yourself and figure out where that force of friction is going to go into and how we can relate that to energy. Because there, I'm going from this ramp down below. So I'm going to have some sort of energy here, but I have this thing kind of sucking some energy out of this block before it gets to point B. Does everybody understand what I want you to do? All right. We'll see you at 10:40. Oh, you don't have a room, Jasper? Oh, Ariel ended up in a room. No, somebody left. All right, so let me send you to room 2. There you go. Okay, so let's think in terms of energy. What energy do I have at point A?
There's gravitational potential energy.
Good. That potential energy. Oops. Otherwise known as mg.
One question.
Oh, I'm not sharing. I'm not sharing.
Okay, I was about to ask.
No. I need that. There we go. I have potential energy. So mgh, the mass of the thing, and we're given that at some given height. Let's see, at point B, what do I have?
You'd have kinetic energy, but it would be less than the gravitational potential because of the friction.
Yes, I agree. Because of friction. So let's see how we can write that out then.
Oh, sorry for so many useless questions, but
No.
for potential energy, should we be notating that as PGE because like we might get into springs and elasticity later?
So I do for spring potential energy to keep them separate. I try to avoid subscripts as much as I can when we get into energy because it gets really confusing. So for spring potential, I always do this.
Okay, cool.
There is no hard and fast rule as to how you must write it. It's just a matter of keeping it straight. Cool.
What energies are we going to learn in this quarter?
So we will do spring potential and height.
Are those going to be the only 2?
Yeah, I'm thinking.
Okay.
Yeah, I'm sorry. I'm trying to discern between the 2 classes. Yeah, so that's I'm 99% sure that's all we do off the top of my head. Yeah. Okay. So let's write this out as an equation because we're going to have one equaling the other. So let's see. Somebody said, I'm going to have potential energy in the beginning. And did you add or subtract something from that, or did you just set it equal to everything on the other side? So I have this plus something equals kinetic or,
You'd have to, potential energy would equal kinetic energy plus like friction energy. I don't know how you calculate that exactly.
so you can go like work due to friction if you want.
Yeah.
Yeah, so there again, there's no hard and fast rule about how you can write these things out. It's just kind of defining for yourself what each of those terms are. So when you are doing the final exam and answering questions, you just need to make sure that I know what your acronyms mean. So define for it somewhere. But I can do that. I can be like, okay, so the work due to friction. So then this is just nothing. But there's also nothing wrong with saying, oops, I'm going to have potential energy. I'm going to lose some of that energy to the work from friction, and that's going to equal my kinetic energy. They're both equally right? So I have some amount of potential from the height. I'm going to lose some of that energy to the work due to friction, and in the end, I'm going to have kinetic energy. Or you can say, I have potential energy, and that's going into two things. It's going to go into my kinetic energy and the work due to friction. The reason why I suggest writing these things out like this is the problem we tend to run into is when we define the force of friction and the work related to it. Remember, for work, we're doing that whole cosine thing. Well, if we look at the direction it's going and use that 180 degrees, and then we get this negative sign, what students tend to do is randomly put that on one side or the other. And so you end up with this negative sign, and then you move it to another side, and suddenly you have friction adding energy in. So what I would tell you, what I highly suggest, is to write out for yourself something that explains actually what physically is going on, and like say it out loud, because that will help you avoid the pitfall of accidentally having friction adding energy into. Does that make sense? Okay, so then I get to the work due to friction. Well, let's see, what is the work due to friction? That is going to be, I see, the force of friction times some distance. And when I see the force due of friction, the one thing I want to do is to remind myself, oh, I need to do forces. So I'm going to have my force of gravity down, my force normal up, perpendicular to the surface. And if this thing is moving that way, the force of friction is going to be opposing that motion. So I'll have a force of friction this way. Why do I want to do that? Because remember, my force of friction is defined as the force normal times mu. So as soon as I see that I have the force of friction, I want to do my sum of forces in the X and the Y to make sure that I am legitimate and my force normal equaling gravity, because remember, it doesn't always. Are we all good with that? Let's see, so I'm going to define up and to the left as positive. So I'll have my force normal minus my force of gravity. And what does that equal? Does that equal 0 or MA?
Should equal 0, because that's just in the Y direction.
Not flying up in the air, not falling down to the ground. So that equals 0. And then my sum in the X, let's see, I only have the force of friction. Oh, you know what? I'm going to stay standard. I don't want to haul around all these negative signs. So force of friction points to the right. I have no other forces. So this thing must equal mass times acceleration. Let's see, and my acceleration then is going to be in the direction of the force of friction. So both of them will have the same sign. If I have one force, that means the acceleration is in the direction of that one force. So I have that, and the force of friction, let's see, then from here I get the force normal equals the force of gravity. So my force of friction is mu times mg from the force normal equals MA, or that mu G equals A. But here, I look at this and I'm like, wait a minute though. What I want the force of friction. So I need to have all of my pieces. When I took out my mass, it's the habit I just get into, and you're like, darn it, I need that thing back. The force of friction is still just the normal times mu. So I started going down a path that is actually not helpful here. I just need this mg times mu to solve my work piece. If you do what I just got ready to do, you take the mass out and you no longer have a force. So make yourself go back and make sure that you're actually putting in the piece that you need. So then I can write this in a different color, that I have the work from friction then is going to be mg mu times whatever distance that patch of friction is. So I can come down here then and say, okay, so I have mgh minus mu mgd equals 1/2 mv squared. Now my masses cancel, totally legit. So I get gh minus, oops, I'm running out of time, mu gd equals 1/2 v squared. So finally, I'm just solving. I want h. I've been given what d is. I've been given what velocity is. So I can move things around, divide by g, and solve for how high that thing needs to be in order to get my desired velocity. Does that make sense? So we are definitely incorporating in everything that we've done so far this quarter, which is kind of cool. Stop recording.